Hi everybody, let's look at this one right here from 2018. It says we've got a large boat like the one shown above, has a mass of MB and can displace a maximum volume of VB. The boat is floating in a river with water of density rho water and is being loaded with steel beams, each of density rho steel and volume V steel. The boat owners want to be able to carry as many beams as possible. Okay, so you've got this boat here and you've got these steel beams, and as you place these steel beams on that boat, it's going to sink further and further into it. We can only displace a certain amount of volume before the boat sinks there. So that is what they're going to ask us about. So they say this: derive an expression for the maximum number, N, of steel beams that can be loaded on the boat without exceeding the maximum displaced volume, which was VB, in terms of the given quantities and physical constants as appropriate. So think about it kind of like this. There's a certain amount of volume we can displace, but you can relate that to a certain amount of mass we can displace. And how much mass can we displace? We are actually looking for the number N of steel beams we can place on there. Well, if we can only displace a certain amount of mass, M I'll call it, then if we divide that by the mass of the steel beams, that should be able to tell us how many steel beams that we can fit in there. Okay, so now to start to figure this out, let's imagine, even when it's floating right on the edge of sinking, that we've got two forces on this boat. We have got here a buoyant force up, and we have got an equal amount of force of gravity down. That's the force of gravity on everything, the boat and all the steel beams as well. So while it's floating, these two are equal to each other. So let's use that to start to solve this problem here. So we know that we've got a force of gravity that is equal to the buoyant force here. This force of gravity, like I said, is the force of gravity of everything. So it is the mass of the boat, and it is this additional mass that we're talking about here, this additional mass due to the beams. So this is the entire mass, and we'll multiply that by gravity to figure out its weight. Then on the buoyant force side, we've got the density of the fluid we're in. I'm just going to write it as rho W instead of rho water, times the volume of the fluid we displace, and they told us that that can be a maximum of VB. So the maximum volume we can displace is VB, and then we multiply by a G on this side as well. Well, one thing that happens is there's a G there and a G there, so those cancel out. So this would be the same solution on any planet here. So now let's figure out this value right here. So we're looking for this mass. This parentheses is now gone because the G's gone, so I can simply say this: the mass we're looking for is the density of water times the volume B that we can displace, and now we just have to subtract this mass of the boat over to the other side there. And so that makes sense. So the mass that we can float is equal to the mass of the water we push out of the way minus the mass of the boat itself. It's sort of the leftover mass. Okay, so now when I said divide by the mass of steel beam, they actually didn't give that to us. But we can do our favorite substitution for mass of this chapter and say that mass of the steel beam is the density of the steel beam times the volume of the steel beam, and they did give us each of those. So now we are basically ready to solve this part of the problem using the same idea here, that this number of beams we can fit is the mass that we can have total, which is down here. And so it is density of water times the volume of the boat that we can displace times the mass of the boat. All of that is basically the total mass we can have, and then we need to divide by the density of steel times the volume of steel. And that will give us how many steel beams can fit on that boat. All right, now, next part. There's actually a different part B potentially on your sheet, but that has to do with thin film interference, and this is just for AP Physics 1 now. And so we're going to skip that. This is actually part C labeled on the piece of paper itself. So it says, later the boat is floating down the river with the water current headed for town. The river has a width of 60 meters here and a constant depth and flows at a speed of 5 kilometers per hour. Partway to the town, the river narrows to a width of 30 meters while its depth remains the same. Calculate the speed of water in this narrow section here. So this is a continuity equation problem. So what we're going to do is right here, we have a width of 60 meters and we're going 5 kilometers per hour. Here we narrow down to 30 meters, they say. So let's use our continuity equation here that says that the area of one section times its velocity is equal to the area of a second section times its velocity. So now area is length times width, right? We can imagine if we look at a side section of this river, it'd be something like this, but the depth is constant. So all we need to worry about is the width there. So I can actually write this. It's the width of section 1 times the velocity of section 1 is equal to the width of section 2 times the velocity of section 2. Because otherwise I'd be multiplying by the depth on each side and that would just cancel back out. All right, so we got 60 meters is our width on one section and our speed is 5 kilometers per hour. So our width in the second section is 30 meters, and so we're looking for that velocity. You could also just think about this proportional reasoning wise. We cut the width in half, so the speed has to double to 10 kilometers per hour. They never say anywhere in here that you have to give it in meters per second, so you can just leave it like that.